Hello and good morning friends, welcome to the CEC Reset live lecture. Dear friends, as you know that we are carrying a series on operations management, and since a very long time we have carried numerous lectures on operations management, and I would like to tell you all that very soon we are going to end up with this particular series, 2-3 more lectures left. But if we talk about today, dear friends, under this very series, that is operations management, today we are going to talk about use of control charts. And dear friends, for this we have again with us in our studios Dr. Subhash Kakkad. As you know that Dr. Kakkad, through this EduSet platform, delivers lectures which helps you in studying your course material, which helps you to understand the world outside the books also. So dear friends, without wasting any time, I would like to welcome our eminent guest, Dr. Subhash Kakkad. Dr. Kakkad, welcome to the EduSet lecture.
Thank you and welcome viewers to today's lecture. And today's lecture is on control charts. It's part of the series of lectures on operations management. And this is regarding the quality control in the operations management. Whether we talk of manufacturing industry or service industry, quality is to be given due importance, without which the operations cannot prolong for a long time. So, we have to devote priority to the quality of the product, quality of the service provided, and quality of the processes. Control charts is a topic regarding the quality. So, today we shall be discussing the quality control charts in detail. We will understand the meaning, concept of these charts, and this study of control charts is based on SPC, statistical process control, and whatever tools are available in SPC, we shall be making use of them in control charts. Quality improvement is nowadays given utmost importance in the organizations. Without quality, one cannot survive, and this is the advantage factor for all the organizations to compete in the market. So, we will be discussing the quality aspect of the product and the services. Let us understand the definition of quality. Quality means fitness for use, quality of design, quality of conformance. Design is there, and then is it conforming to the specifications or not. So, two factors, quality of design and the quality of conformance. Quality is inversely proportional to variability. Soon we shall be discussing the meaning of variability also. Under variations which are applicable and which are there in the product to product, and we shall be discussing how to control the variations. Again, we will discuss one more definition of quality. Degree of excellence a product or service provides a customer is quality. One customer says the quality of a product is its features. The other customer tells me the quality of the product is whether it is good looking or not. Some customers feel that the quality is good if the product is reliable. Quality is good if the product is durable. And even some customers say that quality is good if it is cheap. Different customers perceive the quality in a different way. That is why the definition covers everything. This definition says that the degree of excellence which a product or service provides the customer. Degree of excellence on the factor for which the customer is giving importance to the product or service is of utmost importance. and that factor should be given due importance. And in quality control terms, we call it CTQ, critical to quality. And the factor which is CTQ for a product, for a particular customer, must be given due importance so that customer is satisfied. So, this is the meaning of quality, and nowadays lot of importance is given to the quality improvement techniques. One feels that at all levels quality be maintained if we talk of the processes, if we talk of the product, and even if we talk of service. Quality improvement and statistics. Quality improvement is the reduction of variability in processes and products. What is this variability? In the processes or in the products, we are going to discuss it soon. Unless we understand the meaning of variability, we cannot talk of quality of the product, and we cannot talk of means to control the variability and the quality of a product. Alternatively, quality improvement is also seen as waste reduction. When we talk of quality improvement, it also covers waste reduction. We want to eliminate the waste from the organization altogether, and people have identified 7 different types of waste, and different controls are carried out to eliminate each type of waste so that our organization is waste free or the waste produced is to the minimum level. Quality improvement and statistics, statistical process control, and SQC, statistical quality control, is a collection of tools when used together can result in process stability and variance reduction. We are aiming at process stability. A stable process will give you consistent quality, and we are also looking for reduction in variance of the quality parameters of the product which we are manufacturing. So, identifying the parameters and then finally identifying the factors responsible for these parameters of quality is given due importance, and the tools available in SPC are utilized so that these factors are taken care of and the quality product is produced, quality service is provided. We also know that under quality improvement and statistical process control in the quality management and total quality management, there are simple 7 QC tools are available, and these are histograms, Pareto chart, cause and effect diagram, graphs, control chart, scatter diagram, and check sheet. So, control chart is a tool, is a quality control tool out of 7 available QC tools. When we say that the tools are available which take care of the quality of a product or quality of a service, control charts is one of the tools available to us. And these tools are simple, where not much use of mathematics and statistics is required. A simple knowledge of statistics and mathematics is required to operate the control chart successfully in an organization. Now, we will talk of variation. we will discuss what we mean by variation, axioms and truisms of production. No two items are identical. A production process is going on, a manufacturing process is going on repeatedly, continuously, and these two axioms and truisms tell us the manufactured products, and out of these manufactured products, no two products are made identical. There will be variation in these two products, and extent to which we can measure the variation depends upon the tools of measurement available. But these two products will never be similar. There will be some variation, and these variations we are going to discuss what type of variations are possible. But we have to understand we cannot have two identical products, and the difference will be there, and to what extent this difference we can tolerate, we shall be discussing right now. There are three types of variations in a manufactured product. First one is within a piece, second is piece to piece, and third one is time to time. A production is going on, we are manufacturing product after product. The first type of variation which we are talking about is within a piece. Suppose we are manufacturing a rectangular piece. If it is a rectangular piece, we know that the opposite sides must be equal. And now we are talking about the variation within the piece. If we find that the product and its opposite sides are not equal, then this kind of variation is called within the piece, and the piece will not be exactly rectangular. And second is piece to piece. Same process, we are manufacturing rectangular pieces, and two main important dimensions are length and width. If length of one piece is different from the length of the second piece, then this is called piece to piece variation. One piece is different from the other piece. And third type of variation is time to time. If we start production early in the morning and we check the production which we have in the morning and compare the results with the production which we have in the afternoon and even the production what we have in the evening. If the dimensions are varying from morning to afternoon, afternoon to evening, and evening to morning, and this is called time to time variation. And this can also be discussed on the first day of the month production, next day of the month production. If we compare the results, if there is a variation in the results on these two dates, then this is called time to time variation. So, there are three types of variations: within a piece, piece to piece, and time to time. Variations with respect to process also. We have continuous process and batch process. Variations are possible in a continuous process, variations are also possible in a batch process. Maybe the kind of variations we get in the continuous process are different from batch to batch process, but variations are possible in any type of process. Now we will talk about sources of variation. There are four sources of variation while manufacturing a product: equipment, material, environment, and operation. Equipment is the equipment which is manufacturing the product, and variations are created from the equipment itself, and these variations are called equipment generated variations. Second is material. We are using raw material, we are using semi-finished products, and if the variations are on account of the material used, then these are called material generated variations. And for these kind of variations, the culprit is material being used. Third one is environment variations. The atmosphere under which the production is going on contributes to the variations in the product. Environmental conditions like temperature, humidity, etc. change the parameters of the process being used for manufacturing a product, and the quality of the product changes, and the variations are introduced, and these variations are called environment generated variations. Operation covers the process and the manpower being used. Sometimes the variations are created because of the manpower which is being used for manufacturing the product, and that manpower is also responsible for generating variations. So, there are so many types of variations and the sources of variation. We want identical parts to be produced time to time. For this, we have to control everything. First, we have to identify the variation, and then we have to identify this variation, is it acceptable? If it is not acceptable, we have to find the root cause of the problem, and then we have to eliminate the cause of the problem so that variations generated are eliminated. And control charts are used for identifying the extent of variations in the products or in the services. Sources of variation in production and service processes. There are two types of causes. The first one is called common cause of variation. Random causes that we cannot identify. Unavoidable cause slight differences in process variables like diameter, weight, service time, temperature, etc. If we are running a process, some variations are bound to be there even if everything is under control, and these are called common causes. There is no specific reason for them. Because of the process itself, some variations are there. We go on regular basis on our job to attend the office, to attend the organization, to attend the factory, and the students go to the college to attend the classes. Say for example, a time is fixed, 10 o'clock people are to report to their duty. They start from their home on daily basis, but daily they don't report on duty on a fixed time. Sometimes they are 5 minutes early, sometimes they are 7 minutes early, sometimes they are 3 minutes early, and sometimes 1 minute early. Some variation is there, and this kind of variation is bound to be there, and it is possible. But on the other hand, one day somebody reports, say half an hour late to the duty. On analyzing, it is found that his bike broke down. That is why he is late. Now, we have a specific reason for his coming late, and this reason can be attributed to his late coming, and a cause can be assigned to his late coming. Late coming is unacceptable event, and the reason for late coming is to be identified, and we have an assignable cause to this late coming, and this is breakdown of bike. So, there are variations in the process because of other type of causes, other type of reasons, and those reasons are called assignable causes. Assignable causes of variation, and these causes of variation can be removed also, because these are introduced because of some particular reasons, some particular problem. If that problem is solved, then we are going to get rid of the cause. So, assignable cause can be identified and can be removed, and the common cause is inherent to the process. We are looking for assignable causes, we are not looking for common causes. Assignable causes of variation, causes can be identified and eliminated. Typical causes are poor employee training, worn tool, machine needing repair, and these are assignable causes. We have to identify these causes and to get rid of these causes. So, there are two types of causes, one is common cause and other is assignable cause. Common cause is also called random cause. Random cause we cannot remove, but the assignable cause we can identify and we can remove it also, and we can get rid of this cause. Now, introduction to control charts, basic principles. A process that is operating with only chance causes of variation present is said to be in statistical control. We have already discussed the common causes and the assignable causes. If the process is having only common causes or the random causes, we say that the process is running under statistical process control. A process that is operating in the presence of assignable causes is said to be out of control. So, instead of common causes, if there is an assignable cause, then we say that the process is out of control. The eventual goal of SPC is the elimination of variability in the process. Out of these 3 points, we are responsible for removing assignable causes. So, SPC helps us in identifying a process which is running with assignable causes, and we have to remove this assignable cause, and we need not worry about the random causes or the common cause. Basic principles we are discussing: variables control charts and the attributes control charts. There are two types of control charts we make. We will discuss what exactly is control chart, but first we want to make it clear that there are two types of charts. One is variable control chart, and this variable control chart is, these charts are applied to data that follow a continuous distribution, and if we are able to measure the parameter like temperature, length, width, etc., then we will make use of control charts for variables. On the other hand, the second type of charts, which are called attribute control charts. These charts are applied to data that follow a discrete distribution. The first one is continuous distribution, the second one is discrete. Discrete in the sense, if we say that the results are 1, 2, 3, 4, etc., 1 defective, 2 defective, and this is called discrete. And these kind of charts are called charts for attributes. So, there are two types of charts only when we talk of control charts. Control charts for variables are used to monitor characteristics that can be measured, that is length, weight, diameter, time, etc. Control charts for attributes are used to monitor characteristics that have discrete values and can be counted, that is percentage defective, number of flaws in a chart, number of broken eggs in a box. Where we have discrete numbers, we use attribute charts, where we can measure the parameter, then it is called variable chart. Basic principles of a control chart. This figure shows a typical control chart. What all features are there in the control chart we are going to discuss right now. A typical control chart has control limits set at values such that if the process is in control, nearly all points will lie within the upper control limit and the lower control limit. Now, look at the chart. There is a straight line in the center. This is called center line, and at the top there is one more line which is called upper control limit, and there is one more line below the center line, this is called lower control limit. A dimension is being maintained, manufacturing process is going on. Say for example, we are checking the length, we have a marking for a center line which shows the length we are monitoring. Upper control limit tells us the length up to which we can tolerate, and the lower control limit tells us below the center line how much below we can go, and within this range the products manufactured will be acceptable. Similarly, if we are counting the defects in the manufactured product, there will be a center line, there will be upper control limit, and there will be lower control limit. Say lower control limit is 2, upper control limit is 4. Within this range 2 and 4, if defects found in a product, those will be acceptable. Out of these limits, if something is found, the products will be rejected or the sample will be rejected. So, when a rejection is there, we have to stop the process and see what has gone wrong with the process, and the point is going out of control. And that particular reason or the cause is to be identified and removed, and the process is to be restarted. Again, the points are to be marked on the control chart. Look at this diagram. Control charts show sample data plotted on a graph with center line CL, upper control limit UCL, and lower control limit LCL. A typical product is being manufactured. Center line, we are looking for 16 millimeter diameter. A rod is being manufactured, and the diameter we are looking for is 16 millimeter, and this is center line, and it is acceptable in the range of 15.8 to 16.2, means 16 plus minus 2 millimeter is the specification. So, lower limit on the diameter is 15.8, and the upper limit on the diameter is 16.2. Within this range, the rods will be accepted, and out of this range, the rods will be rejected. Now, every time we are checking the rod and its diameter is being marked on the control chart, we see that first one is within the limit, second is also within the limit, even first, second, third, fourth and fifth, they are all within the control limits, but the sixth point is out of control, and this observation going out of control. At this particular point, sixth point, the process is out of control. Up to 5 points, the process is under control. When it goes out of control, we have to find out the reason for the process going out of control. And this is the use of control charts. Control charts, we have 3 lines, center line, upper control limit and lower control limit, and the points are being marked at regular intervals. We are taking a sample of 5 pieces and we are marking the mean at every time we take the sample, and we see that whether the sample mean is within the control or not. When it is within the control, the process is said to be under control. When it goes out of the limits, then we say that the process has gone out of control. Now, how to set control limits? Whenever manufacturing is being done, no assignable cause is there, only common causes are there, and the process will follow normal curve with plus minus 3 sigma, and plus minus 3 sigma means 99.73% products will be manufactured within this range. Only 0.27% defective will be produced. And if we talk of ppm, only 2600 ppm will be out of these limits, plus minus 3 sigma. And if we mark the plus minus 6 sigma limits also on this normal curve, only 3.4 ppm will be in the rejection range. So, plus minus 6 sigma, 3.4 ppm rejection, plus minus 3 sigma, 2600 ppm rejection. Now, look at the diagram again. Say our specifications are marked on plus minus 6 sigma limits, and our process is running at plus minus 3 sigma. Then our rejection will be only 3.4, because the items going out of specified limits will be only 3.4 ppm. That is why, that is the meaning of 6 sigma process. Introduction to control charts, basic principles. Say for example, process is going on, input is there and output is there, and from the output we are taking a sample and we are checking the parameter, we are putting the results on the control chart. Then we have to detect assignable cause and identify root cause of problem. If assignable cause is checked or detected, then we have to find the root cause of the problem, then the implement corrective action and verify and follow up. This is the way the control charts operate, and to get rid of the assignable causes. We will repeat basic principles. Input, process is there, we get the output. From the output we take a sample and we put it on the results on the control chart, and the control chart tell us whether the process is under control or it is out of control. If it is out of control, we have to identify, we have to detect the assignable cause for the process going out of control, and then we have to identify root cause of the problem and implement corrective action to get rid of the root cause of the problem, and then we have to verify and follow up through the control chart. This is the way we use the control charts. General model for a control chart. Let W be a sample statistic that measures some quality characteristic of interest, and suppose that the mean of W is mu W and the standard deviation of W is sigma W. Then the center line CL, the upper control limit UCL and the lower control limit LCL become as follows. UCL will be mu W plus K times sigma W. CL of course will be mu W, and LCL will be mu W minus K times sigma W, where K is the distance of the control limit from the center line expressed in standard deviation units. So, this is the way to calculate the LCL and UCL and mark it on the control chart. Important uses of the control chart. Most processes do not operate in a state of statistical control. Consequently, the routine and attentive use of control charts will identify assignable causes. If these causes can be eliminated from the process, variability will be reduced and the process will be improved. The control chart only detects assignable causes. Management, operator and engineering action will be necessary to eliminate the assignable causes. Popularity of control charts. Control charts are a proven technique for improving productivity. Control charts are effective in defect prevention. Control charts prevent unnecessary process adjustments, and control charts provide diagnostic information. Control charts provide information about process capability also. Now, design of control chart. We will discuss how the control chart is designed. Suppose we have a process that we assume the true process mean is called mu, which is equal to 74 units, and the process standard deviation sigma is 0.01. Samples of size 5 are taken, giving a standard deviation of the sample average sigma x bar is equal to sigma divided by root n, where n is the sample size. In our case, it is 5.01 divided by root 5 is 0.0045. So, this is sigma x means, sigma of the sample means. Now, control limits can be set at 3 standard deviations from the mean in both directions. 3 sigma control limits, UCL 74 plus 3 times 0.0045, which is equal to 74.0135. Of course, center line CL is 74, LCL is 74 minus 3 into 0.0045, which is equal to 73.9865. Now, we have all the 3 parameters: center line, upper control limit and lower control limit. And now, we will draw the control chart also. Designing of a control chart. Now, on this graph, we mark the center line at 74, upper control line at 74.0135 and the lower control limit at 73.9865. So, we have all the 3 lines and we will start taking the samples from the running process. Every time a sample of 5 pieces is taken and average is also calculated in each sample, and the average is marked on this control chart. Luckily, whatever is drawn in this diagram, all the points are within the control limits. So, we can say that the process is under control. Choosing the control limit is equivalent to setting up the critical region for hypothesis testing. In this process, we are testing the hypothesis as null hypothesis H naught is mu is equal to 74 and the alternate hypothesis is mu is not equal to 74. So, control charts nothing but testing the hypothesis, and hypothesis has been made here for the control chart what we show in the previous slide. The null hypothesis is mu is equal to 74 and the alternate is H1 which is mu is not equal to 74. An alternative method, instead of calculating sigma etc., an alternative method is also available. An alternative method for the x bar chart using r bar and the A2 factor etc. So, there are 2 charts available, x bar and the r is the range. In the sample, say for example, we have taken a sample of 5 pieces, mean is to be marked on the x bar chart and the range is to be marked on the r chart, and these 2 charts x bar and r chart are to be seen simultaneously. In both of the charts, the observation should be within the control limits. Even if in one of the control charts it is out of the control limits, we have to stop the process and find out the assignable cause. In this slide, an alternative method is being explained, where we make use of the factors like A2, D3 and D4. Use this method when sigma for the process distribution is not known. Use factor A2 from the adjacent table, and this table gives 4 columns. The first column gives you the sample size, second column gives the factor A2, third column gives D3 factor and the fourth column gives D4 factor. Against the sample size, we have to read A2, D3, D4, and we have to make use of these factors in calculating the upper control limit and lower control limit. We will explain how to do it. Say for example, step 1, calculate the range of each sample and average range. Time 1, time 2, time 3, observation 1, 2, 3, 4, and the readings are taken, and each time we have to take the range. Range has been calculated at time 1, 0.2, time 2, 0.3 and time 3 again 0.2, and average range is taken r bar. Summation of all these 3 readings and divide by 3, which gives us 0.233. It is a r bar. Mean of the range is 0.233. And step 2, calculate center line, upper control limit and lower control limit. Center line x bar, and this is x double bar. X double bar gives us the grand mean. Already we have calculated the means 15.875, 15.975 and 15.9 and divided it by 3, we get the grand mean as 15.92. So, x double bar or the center line is 15.92. The upper control limit for x bar is x double bar plus A2 r bar. A2 is the factor taken from the previous table and r bar is the mean already calculated for range. This is 15.92 plus 0.73 into 0.233, and this gives 16.09. 0.73 has been taken from the previous table. Let us go to the previous table. A2, which has been 0.73 for a sample size of 4. So, our sample size here is 4 and the A2 factor is 0.73. So, 0.73 is the value for A2 for a sample size of 4. Our sample size is 4 now. The lower control limit is x double bar minus A2 r bar 15.92 minus 0.73 into 0.233, which is 15.75. And similarly, control chart for range R chart. We have to make a control chart for range also. Center line for range R bar we have already calculated 0.233 is the center line. Upper control limit, and under this we will use D4. D4 is D4 against a sample size of 4 is 2.28 from the corresponding table, and 2.28 multiplied by 0.233, which is equal to 0.53. And similarly, lower control limit for the range is D3 R bar, and D3 in this case is 0 for a sample size of 4. So, lower control limit is 0. So, we will draw a control chart for range also with center line at 0.233, upper control limit at 0.53 and lower control limit at 0. And this is R bar control chart. We found X bar within the control, and now we find that even the readings of range also are within the control. So, we can say that the process is under control. So, we are drawing the control charts for variables, and in variables two charts we have to prepare, one is X bar, other is R. So, X bar and R chart are important when we talk of charts for variables, and we have to see that the point should be within control on both the charts simultaneously. Even if one of the charts shows that the point is out of control, then we have to stop the process and look for the assignable causes, and we have to get rid of the assignable cause and then follow the process again. Rational subgroups. Subgroups or samples should be selected so that if assignable causes are present, the chance for differences between subgroups will be maximized, while the chance of differences due to these assignable causes within a subgroup will be minimized. Constructing rational subgroups. Select consecutive units of production provides a snapshot of the process, good at detecting process shifts. If you are taking regular readings, we can identify the process shift also. Select a random sample over the entire sampling interval, good at detecting if mean has shifted. Out of control and then back in control, because we are getting rid of the assignable cause. We are identifying, we are detecting the assignable cause, we are getting rid of the assignable cause, and then we are setting the process in control. Look for runs. This is a sequence of observations of the same type, all above the center line or all below the center line. Now, we have to see the points marked on the control charts, and this will give us the trend in the production. Runs of say 8 observations or more could indicate an out of control situation. Maybe the points are within the control, but they are in one direction only. Say from lower range, all the points are being marked towards the upper range, then it shows the dimensions are changing, increasing. So, again we have to look for the reason. Run down, a series of observations are decreasing, run up is a series of observations are increasing, and these are the reasons for concern also. Analysis of patterns and control charts. This shows a control chart, and we have to see at different points, sometimes we are getting the increasing results and sometimes we are getting the decreasing results, though the points are within the control, though we say that the process is under control, but there are changes being observed in the process. analysis of patterns on control chart. These kind of patterns are also available on the control charts. Analysis of patterns on control chart. Here again, these kind of patterns, lower control limit, mu is there, upper control limit is there, lower specified limit is there, upper specified limit is there, and these two different diagrams are observed on the process. Now, analysis of patterns on control charts, we will have some rules. We are going to discuss those rules, and following rules would signal that the process is out of control. If either one point plots outside 3 sigma control limits, then we can say that the process is out of control. 2 points of 3 consecutive points plot beyond a 2 sigma limit, then it is also a point of concern. 4 out of 5 consecutive points plot at a distance of 1 sigma or beyond from the center line. This is also a point for concern. 8 consecutive points plot on one side of the center line. Again, this is a point for concern. Something is going wrong in the process, and the process is going to be out of control soon. We have to stop the process and see that what is going wrong in the process, what is the assignable cause, and we have to find an effective solution to remove the assignable cause. And this is also a control chart. It tells us something. It tells us something, what is the way the process is running. X bar and R control charts will repeat. Grand mean be X double bar. Let the sample mean for the ith sample be X bar I. Then we estimate the mean of the population mu by the grand mean X double bar, which is equal to 1 divided by m sigma 1 to m X bar I. And similarly, average range and estimator of sigma R bar is equal to 1 divided by m and summation I from 1 to m R I. Be the average range, then R bar is an estimator of mu R and an estimator of sigma. Sigma is equal to R bar divided by T2, and here we have to see that it is not sigma, it is sigma hat. Sigma hat is equal to R bar divided by D2, D2 is the factor. Similarly, for X bar control chart, we say that upper control limit is X double bar, which is grand mean plus A2 R bar. Center line is X double bar, and lower control limit is X double bar minus A2 R bar, where the constant A2 is tabulated for various sample sizes. And these factors like A2, D3 and D4 are available in our books. At the end of the book, we are given certain tables which are part of the book itself, and these factors like A2, D3, D4 are available in the books, and we can make use of these tables in designing the control charts. Similarly, for R control chart, UCL is D4 R bar and center line is R bar only, and the lower control limit is D3 R bar. Once again, these D4, D3 are available in the books. Now, look at this control chart and the data available. Data have been collected. A sample is taken every time of 5 pieces, and dimensions are recorded. And say for first reading, and these observations are 33, 29, 31, 32 and 33. These 5 readings, and the average is means X bar is 31.6, and if we see the range is 4. A number of observations are taken, and then against all these observations X bar and R is calculated, and finally X double bar means grand mean is calculated and R bar is calculated. If we see the X double bar means grand mean is 33.32 and R bar is 5.8. and on the control chart, central line is marked on 33.32 because it is the grand mean, and similarly upper control limit and lower control limit as 36.67 and 29.97 using the values A2 are marked. Similarly, for the range also, lower control limit is 0, R bar is 5.8 as we have calculated, upper control limit for the range is 12.27, it is marked. Now, looking at the control charts, we find that there are certain points which are out of control. If we see the X bar chart, 2 points are above control limit, upper control limit, and 2 points are below lower control limit, and it means the process is not under control. We have to see for the assignable causes, and similar to the control chart for range also. One of the points is going above the upper control limit. So, we have to see the reason for this point going out of control. So, viewers, today we discussed the variation, the meaning of variation, variation in the production, causes of variation. There are two types of causes, assignable causes and the random causes, and we are to look for assignable causes in the process. We have to identify the point at which the assignable cause has occurred in the process, and this is detected by use of control charts. There are two types of control charts for variables and control charts for attributes. Today we discussed control charts for variables, and these are X bar and R charts. We have to see them simultaneously. I hope I am able to make this thing clear to the viewers, the use of control charts. Thank you for listening patiently. Thank you so much.
Thank you, sir. Thank you so very much for giving us once again a very productive session. Dear friends, if you want to give your feedback regarding this particular lecture, then you can mail us at info.cc@nic.in. We would be meeting again with different topic. Till then, thank you. Thank you, sir. Thank you so very much.